Before electricity can arrive at your home to light your room and heat your food, it has to be made first. Electricity is generated at power plants which could be located miles of distance from your home or office. Basic sources of electricity include water in high dams, geothermal energy, wind power, tidal waves in seas, and nuclear energy, amongst others. The electricity generated at a power station is transmitted to consumers such as factories, institutions, and homes by overhead or underground cables. All power stations in a country are linked together by cables, and the power then distributed to the consumers. This ensures that the power is available to the consumers even when one of the power stations is shut down. This system of power cables connecting all the stations in a country to each other and finally to the consumers is called the national grid system. Power stations generate electricity, usually alternating current at between 10 and 30 kilovolts. This voltage is then stepped up to between 130 to 400 kilovolts for transmission, so it lives at its most powerful form. In comparison, when it gets to your wall outlet, it's just about 120 or 240 volts. From the power plant, transmission lines carry electricity long distances from city to city or from town to town. And these lines are held up by transmission towers, which are the big structures you've seen along the highways. These towers are about 100 feet tall and can be made of either metal or wood. Transmission lines are actually bare aluminum or copper wires, which are conductors of electricity. They are thick to reduce resistance. Porcelain insulators hold the wires in place and keep electricity running through the wires and not through the tower itself. In addition to these wires carrying electricity, 1 or 2 ground wires protect the tower from lightning strike. These bare wires are not, however, safe to touch at any time. Before electricity can travel from the transmission to your home, it has to make a stop at a substation like this. A substation is enclosed by fencing for safety and houses the equipment that change the electricity from one level to another. The electricity coming from the transmission lines runs through a substation transformer which steps down the voltage to less than 38 kilovolts. This low voltage electricity is easier to handle. However, this low voltage is still high for consumers and is stepped down to appropriate values for domestic and industrial use. This comprises the distribution system. So after electricity has been made and transmitted to your city, it is now time to be distributed to homes and industries or businesses. The distribution system carries electricity at lower levels for shorter distances from town to town or from neighborhood to neighborhood. Like a transmission system, these smaller distribution wires are held up by distribution poles or buried underground. The poles are typically 50 feet high and are mostly made of wood. At the top of the pole are the primary or main wires. These wires are coming from a nearby substation and can carry anywhere between 34.5 to 7.2 kilovolts, but the most common is 12 kilovolts. If the electricity is going to a home, there is typically just one wire. If going to a factory, there would be 3 wires because factories and businesses usually need more electricity than homes. These primary or main wires are often held up on the pole by a cross arm. The wires are held in place by insulators, which help to keep the cross arm and the pole from becoming energized by the wire. Another equipment found on a distribution pole is the lightning arrestor. This is similar to a surge protector in your home. It protects the pole equipment from being harmed by lightning. At about the same level is the cutout. A cutout is similar to a fuse in your home. It protects the pole and the equipment from too much electricity. If an object like a tree branch would come in contact with the wire, the cutout would open, indicating a problem with that section of the line. Below the cutout is a piece of equipment that looks like a can. This is a transformer. It takes electricity from the wires at the top and steps down the voltage to a level needed by the consumer. Remember, wires can be on a pole or buried underground. If the primary wires are underground, then the transformer is the green box in the backyard. So if you have overhead lines, you will have a pole and a transformer. If you have underground lines, you will have a green box on the ground. Below the transformer is another wire called the neutral wire. This doesn't mean it is safe to touch. The neutral wire is the return line that goes back to the substation and helps to balance the amount of electricity out on the system. Without a neutral wire, our appliances could get too much or too little electricity, which could cause damage. On your screen is a schematic representation of the transmission system. Dangers of high voltage transmission. The dangers of high voltage transmission include 1. The risk of electric shock in case poles collapse or cables hang too low. 2. The risk of fire on nearby structures and vegetation when the cables get too close. And 3. The harmful effects of strong electric fields. Let us look at power losses during transmission. The power dissipated in a circuit is given by P is equal to VI. But then V is equal to IR according to Ohm's law. And therefore, P is equal to I squared R, where I, V and R are current, voltage and resistance respectively. What this means is that for a given resistance in a circuit, when the current is high, the power loss is large, and when the current is low, the power loss is small. Power loss in a transmission cable is therefore low when it is transmitted at high voltage and low current. The output voltage from a power station is therefore stepped up for long-distance transmission in order to minimize power losses in transmission cables. Since long distances are involved, transmission cables are thick and made up of materials which are good conductors of electricity to minimize resistance. Aluminium is preferred because it is a good conductor, it is light and cheaply available compared to copper. For example, the resistance of a length of a power transmitting cable is 10 ohms and is used to transmit 11 kilovolts at a current of 1 amperes. If this voltage is stepped up to 160 kilovolts by a transformer, determine the power loss. Now, assuming the transformer is 100% efficient, power input is equal to power output. V1I1 is equal to V2I2. 11,000 times 1 is equal to 160,000 times I2. I2 is equal to 11,000 over 160,000. That gives us 0.069 amperes. Power loss is given by I squared R. If we multiply that, we get 0.048 watts. Now suppose the power was transmitted at the 11 kilovolts and a current of 1 amperes. Let's find power loss. Power loss is given by I squared R. 1 squared times 10 gives us 10 watts. This shows that when the voltage is stepped up from 11,000 volts to 160,000 volts, the power loss is reduced by over 200 times. Let us now look at how the electrical system works in your home. Power flows from your service provider through a series of high voltage wires. Transformers reduce the voltage to 240 volts as it enters your house. At the service head, a meter records the amount of power you use. In most homes, service comes in two wires, a live and a neutral. The live wire carries 240 volts, runs to the main switch and down to the bus bar, being the link of the main panel. Individual circuits connected to one of these bars supply 240 volts to the switches and outlets in your house. Each circuit is connected by a circuit breaker which trips, stopping the flow if the circuit becomes overloaded. Electricity travels in a loop or a circuit. Once the circuit is broken, either by a circuit breaker, a switch or a fuse, the current ceases. The current enters through the live wire, usually red or brown, and returns via the neutral wire, usually black or blue. Most systems will have an earth wire, either green, yellow, or bare copper wire. This is connected to the neutral bound service panel, which is directed on a path to the ground. When an overload happens and the breaker is tripped, the current is discharged to the earth. A number of switches and outlets will be connected to the circuit in your home, although some heavy users such as refrigerators may have their own dedicated circuits. The current is carried by insulated copper wires throughout your house. The larger the wire, the more the current they can carry. If a wire uses more current than it's ready for, it will overheat. That's why a sensitive circuit breaker is so important. A switch completes the circuit when it's turned on and interrupts it when it is shut out. This is a schematic representation of the consumer fuse box. It consists of the following. The live bus bar. This is a brass bar connected to the live wire through the main switch. The live wire of each circuit is connected to it through a fuse. Neutral bus bar. This is a brass bar to which all the neutral wires of such circuits are connected. And finally, earth terminal. The terminal may be a bus bar or a part of the fuse box if it is metallic. Whichever the case, the terminal is earthed either through water piping or through a thick copper bar buried deep in the earth. Again, this is a schematic representation of the distribution of power from the consumer unit. Each component of the above circuit has a wire running from the live bus bar through an appropriate fuse or circuit breaker and a return wire running from the neutral bus bar to the output terminal. Except for the lighting circuit, other circuits have an earth connection running from the earth terminal to the outlet socket. Appliances that require earthing are automatically earthed through the socket, making them safe to handle. When such appliances are not earthed, there is always the danger of electric shock. In the lighting circuit, the lamps are connected in parallel so that they operate at the same main voltage and can be operated independently. The switches are on the live line for safety. If the switch were to be on the neutral line, the live wire would still remain at the same mains potential even when the switch is off. This would cause an electric shock when one handles any conductor linked to the live wire. The cooker and water heaters are usually supplied with their own circuit. These circuits are earthed and their wires are relatively thicker than those of the lighting circuit since they carry large currents. The two-way switch circuit. This is a circuit in which a lamp can be operated by any one of two switches. It can be put on by one switch and put off by the other, and vice versa. The arrangement is convenient in lighting of a staircase and corridors. A switch at the bottom of the staircase can be used to put on the light, which can then be put off when one gets to the top of the staircase. Similarly, a lamp can be put on by a switch at the door of a room and put off by another switch at the other end of the room. Fuses. Fuses are used to safeguard against excess currents in a circuit. A fuse consists of two metallic terminals fixed to a holder. A thin length of a fuse wire is stretched between these terminals. This type of a fuse is used to protect appliances that are highly sensitive to current fluctuations. If by any chance a high current passes through the appliance, the fuse wire melts, breaking the circuit. A 3-pin plug. The insulation of the 3 leads of a power circuit appliances are colored distinctly so that they link correctly when connected to the power circuit. The live lead is colored red or brown. The neutral is colored blue or black, while the earth is colored green or green with yellow stripes. A 3-pin plug has the letters L, N, and E marked on the live, neutral, and earth pins respectively. The 3 leads from the appliances are connected to the 3 pins at the plug as shown on your screen. A fuse is used in the plug to safeguard the appliance from damage due to excess currents in the circuit. The rating of the fuse used depends on the operating current of the appliance. The value of the chosen fuse should always be slightly above the value of the operating current of the appliance. The common values are 2 amps, 5 amps, and 13 amps. For an appliance operating at 4 amps, the most appropriate fuse would be the 5 amps one, while the 13 amps fuse would be suitable for an appliance operating at 11 amps. Electrical energy consumption and costing. The kilowatt hour. Commercial companies charge for electrical energy supplied to consumers. The amount of energy used by the consumer depends on the power rating of the appliances used and the time for which they have been in use. Energy is equal to power times time. The SI unit of energy is joule. This unit is too small for measuring the large amounts of electrical energy used in homes. The unit for costing of electrical energy is the kilowatt hour. The kilowatt hour is the electrical energy spent in 1 hour at the rate of 1000 joules per second or watts. Recall that 1 watt is equal to 1 joule per second. 1 kilowatt is equal to 1000 joules per second, which is equal to 1000 watts. Total energy spent is given by power times time. 1 kilowatt hour is equal to 1000 joules per second times 1 hour. That is 1000 joules per second times 60 times 60, which again gives us 3.6 times 10 to the power 6 joules or 3.6 megajoules. We take an example. An iron box rated 3000 watts is used continuously for 45 minutes per hour per day. Calculate the power cost per week at the rate of 6 shillings and 70 cents per unit. In the solution, number of kilowatts is given by 3000 over 1000, which is equal to 3.0 kilowatts. Number of kilowatt hour per day is equal to 3 times 3/4, that is 45 minutes, that's 3/4 of an hour, times 1 hour times 24. Number of kilowatt hour per week is equal to 3 times 3/4 times 24 times 7 days. That gives us 378 kilowatt hour. Cost per week is 378 times 6.7, which gives us 2,532 and 60 cents.
The battery, of course, is now 200 years old and was discovered, it is said, by a fellow by the name of Aloisio Galvani, an Italian. Galvani was in fact lecturing to some of his pupils. He was a lecturer in medicine. Mrs. Galvani was standing in the one end of the room and she was preparing the evening meal because this was done at his home. And Mrs. Galvani was busy attentively listening to her husband, but also skinning the frog's legs. She noticed that when she touched the frog's legs, a twitch occurred. She called her husband over and said, "Have a look at this interesting phenomenon." And Aloisio Galvani came along, looked at the frog's leg, saw the twitch and said, "Wife, what a magnificent discovery I've made." Luigi Galvani wrote a letter to his friend Alessandro Volta. Volta was not a physician. He was what we would today call a physicist, or in those days they were known as natural philosophers. And what Volta did was decided to set up the experiment Els Galvani had done, and realized very quickly that what had been discovered was not the essence of life, but some form of energy. And of course this was electrical energy. Now you see, the people of the day were not completely unaware of electricity. Electricity was known in the 1700s in the form of static electricity. Cornelius at Leiden University in Holland had done various experiments and in fact came up with a device known as the Leyden jar, the only device that was known at the time for the storage of electricity. The problem with this is it was static electricity. The experiments are always very brief in nature because of the short duration of the spark. The voltage is always high, so some of the experiments are a little painful and there's not much else you can do with it. These two Italians, they came along and they found that by the use of certain dissimilar metals and chemicals, you could generate electrical power on demand, at will. This opened up a whole new vista for research within the field of technology and science.